see, Tanya. Today we're going to cover kind of a variety of topics to finish up describing the microstructures of materials. And I've gathered these under a general heading of macromolecular solids because here we're concerned about things that are made up of building blocks much larger than single atoms. We'll talk about polymeric solids, which include usual organics and plastics, silicates, which are the rocks and minerals, fibers, which are fibers that we use in fabrics and in fiber composites and such things, and finally a little bit about the lipid bilayer as an example of a biological application, biological molecules. Finally, I'll say just a word or two about quasicrystals. Of course, particularly polymeric solids, biological molecules, silicates maybe over in the geology department. These are subjects of entire courses elsewhere on the campus, so I'm going to be very superficial and very brief in the discussion of all of them because we just really need to know what they are in the context of this course. First of all, the polymeric solids. Well, you know about polymers. The simplest kind of polymer is the chain polymer, where we take a basic unit, in this case methane, CH4, carbon with 4 hydrogens attached to it, and duplicate it out to form very large chains. The carbon, of course, has valence 4. Each hydrogen atom has a single valence electron, so CH4 is a sealed, a neutral compound. A very uninteresting compound in many ways because it has no dipole moment, no dangling bonds, not much can happen with it. However, what you can do with it is you can break the bond between carbon and hydrogen, attach another carbon, and then you have C2H6, which is ethane. If you attach another carbon to that, you can produce the 3-carbon backbone chain, which is propane, and finally just bringing it all out into an arbitrarily long chain, you can have polyethylene. And there is no requirement on how short this chain can be. I can do this indefinitely and create chains that literally have thousands of mers or individual carbon atoms in them. And this is kind of the basic thing that's going on in a polymer or an organic molecule. The important polymers are almost all carbohydrates. We can make some simple compounds that have silicon in place of carbon, but there's a problem with that that restricts those compounds. I'll tell you about in just a minute. The chain polymer can be elaborated in many, many different ways. For example, we can take the carbon and replace the hydrogens that in the chain by making a double bond between the carbon atoms. So in this case, I have 2 carbons double bonded to one another. I can then replace one of the hydrogens by some group, some other atom or some other group. This could be another atom like fluorine, or it could be an entire group of atoms, such as you see down here at the bottom, to elaborate this kind of chain. Then I can, of course, build a chain by breaking this double bond and attaching the carbon to other carbon atoms, repeating this mirror as often as I want to in both directions. Incidentally, right here is the example of why we have a huge variety of polymeric or organic molecules that are based on carbon and the carbon backbone. There are a few such compounds that are based on silicon, but the so-called silicones. People often talk about the Silicon Valley, which it is, but it's Silicon Valley. Silicone is a chain polymer using silicon instead of carbon as its backbone. And there are quite a few silicones out there on the market. They have a useful high temperature stability, high temperature engine oils and such things, greases can be silicone-based. However, you cannot get the complexity with silicon that you can with carbon. And it was only recently that people really realized why that was true. Some theoretical physicists got to working, and what they found basically from first principles was why it is that it's almost impossible to form a double bond between silicon atoms. An awful lot of organic molecules, or the building blocks for organic molecules, are based on the fact that we can form double bonds between the carbons. Well, silicon is just far enough down in the periodic table, and has just enough electrons in its inner shell that you just can't get an effective double bond in silicon. And that's the reason that the silicon organics, if you want, silicon-based organics are much more restricted than the carbon-based organics. Germanium also has the same structure as carbon and silicon, but to my knowledge, there are no germanium-based organics at all. And this basic bonding in carbon is a good reason for that. Well, the things that we can replace this hydrogen with can make a rather dramatic change in the properties of the molecule. If I replace the hydrogen with fluorine and produce fluorines everywhere, then I get tetrafluoroethylene, which is the basic building block for Teflon. This is an extremely inert molecule. The fluorine being a big group 7 atom pretty much seals off the molecule. There's no dipole moment in this configuration, even when I make it very long. So I get a material that is very inert. And you know that we use the inert properties of Teflon rather widely. We use it as coatings and frying pans and for all sorts of other surfaces where we want very low friction between the two surfaces. Well, we really won't say that much about friction in this course.
Is it something like Teflon tape that would seal?
Sure, very, yes, and that's the same thing. It's very inert. Not going to corrode away. It's chemically inert. It's low friction. You can wrap it up easily, and it's very effective for these kinds of purposes. This is why does something like this have very low friction? Well, we don't really talk about friction and mechanical properties in this course, but basically there are several sources of friction, but the ultimate source of friction, the friction between two surfaces, is a transient bonding between the two surfaces. The bonding can be of a chemical type, but particularly it can be of a dipole type. And it can be a relatively strong bond if the thing in the surface has dipole moments, because those dipoles can interact with whatever the other surface is and bond them together. And in fact, if you look at two surfaces after you've rubbed them across one another, should have brought a picture, but I didn't. What you'll see on the surface, you'll see little places where the two surfaces have adhered together. You've actually pulled out pieces of one material and left it on the other. And it's that sticking and pulling out that is the cause of significant friction between the two surfaces. Now, if I get something that's really, really inert, like this Teflon, and that has no dipole moment embedded in it, then I get something that has a very, very low friction. And as a consequence, it's very useful for those surfaces. It also, things don't stick to it very well because it doesn't bond very well to anything. So it's a great material for non-stick frying pan surfaces and other things of that sort. We will talk about that a little later. Lucite, the old commercial, lucite turns you loose. It's invented by a fellow I knew actually back at General Electric Research Laboratory back in the 1950s. Lucite, we put a more complicated grouping associated with the carbon and then multiply this chain out in space. Because of this kind of dangling cluster, because of the possibility of doing other bonding and so on, if I make up a solid out of this material, it is a rather strong material. It's simple plastics, although it's relatively strong, you know lucite. But its real advantage is that it is a very nice, it combines some mechanical strength with optical transparency. There are in fact things much better than lucite these days for that purpose, but the combination of strength and transparency. In fact, someone asked me, might have been you after class last time, what we made bulletproof glass out of. Let me reestablish my thing here. And the answer is what we call bulletproof glass these days is not glass at all. It's plastic of one kind or another. And that plastic has to combine high strength to resist projectiles with translucency, so you can see through it. And lucite was the original prototype of a strong, transparent plastic. We now have things, the polycarbonates that are much, much better than this. The properties of polymers are adjusted by controlling, if you want, the substructure of the polymer. And there are a whole variety of ways to do that. And I'm just going to kind of go through systematically what they are. Suppose we have a polymer chain here, and we add on another atom or a group of atoms just as I described. Well, there's several different ways to do that. We can take all of our atoms and we can put them on one side. We can take, which is called an isotactic configuration. We can take these atoms and we can alternate them back and forth across the polymer, which is called a syndiotactic configuration, or we can just put them on randomly, which is called an atactic configuration. Now, this is going to have a rather big effect on the chemical properties of the polymer are largely determined by the composition, that is how many of these radicals and what their nature is we put down. But the mechanical properties of the polymer are going to be very sensitive to the configuration of the polymer. Let me just look at this. If I have all of these radicals on one side of the polymer, these things are certainly bigger than hydrogen. What I'm going to wind up getting is just a bending. So an isotactic polymer is going to wind up in a spiral because it's constantly trying to bend around in order to make room for these unusual atoms. A syndiotactic polymer, on the other hand, is going to be a zigzag. And as a zigzag, it can be relatively straight. So if I make a solid by packing these things together, I will get a rather different configuration in the solid and properties of the solid with an isotactic polymer than I will a syndiotactic polymer, even if the composition is exactly the same. This thing will tend to crystallize because these strains are relatively straight and they can line up. This will tend to be non-crystalline unless I can find a way to pack several of these together with a simultaneous spiral, which you get in DNA, for example. But usually this will be a non-crystalline kind of material. ATAC is even less likely to be crystalline because it has bends and twists and such all over it in a very regular shape. Similarly, this is particularly important when the radical that I put on is a larger group, and is particularly important in the molecules cis polyisoprene, which is the basic building block of rubber, as versus trans polyisoprene, which is gutta-percha. If I look at the configuration right around an internal double bond in the material, and if I have a radical sitting there, then there are two ways that I can configure it. I can configure it and the neighboring hydrogen on the same side of the double bond, which is what happens in rubber, or I can have them on the opposite side of the double bond, which is what happens in gutta-percha. Interestingly, both of these materials give rise to molecules that have certain elastomeric properties. Gutta-percha naturally comes out as a kind of rubbery substance. And it's amazing how many of the materials breakthroughs in the history of the world were first really used in golf courses. In the late 19th century, before we got good rubber, golf balls were made of gutta-percha. This rubber, on the other hand, because of the severe kinks in this chain, natural rubber is not really a very solid substance at all. It's almost gummy. The molecules are kinked, twisted, cocked. They don't fit very well together. As a consequence, rubber consists of a whole bunch of kind of independent strands that when you pull on them, move over one another rather easily. It was useful at an early stage for pencil erasers, which is what's called rubber. It was also used for rain coverings, sort of soft things that you would put over your shoes, which were called rubbers. And this was where the name came from, rubber, because it would rub out pencil marks. But it was not a very effective structural material at all. And it's because of this configuration, which produces a very kinked molecule, and adjacent molecules just don't pack very well together. I'll tell you how we solve that problem in just a minute. You can also have order in polymers along the length of the polymer. Suppose I have two different MERs that join together, a MER of type A and a MER of type B. They can be used to form more complex chains in various ways. I can have a random copolymer in which the A's and B's are randomly distributed in some stoichiometric combination. I can have regular copolymers in which they alternate quite strictly. This is the polymeric analog of an ordered crystal. Or I can have block copolymers in which I have a long strip of A, a long strip of B, and then back to a long strip of A again. And obviously, these will have different applications. The block copolymers can be particularly useful because this part of the polymer will have one set of chemical properties, and this part can be given a very different set of chemical properties. So that if I put this into put it in a membrane, maybe A's don't like the membrane, B's do, in which case this thing will penetrate the membrane and get stuck on the membrane because the B part of the copolymer will get stuck there and stay there. And there are a whole bunch of biological molecules that work in that way. I'll show you some examples in a moment. Branched copolymers. In this case, I can have a backbone that may be A with the B's branching off of it to form things that look like this. Well, if you just look at this structure, you say, wow, this might be a rather good structure for a chain polymer that has some mechanical integrity to it. Because I get a bunch of these things. If I get a bunch of just strands and put them together, then they will kind of be like strands of spaghetti in a plate. I pull on the plate, the strands of spaghetti can just pull over one another, and I can get considerable weakness or deformation in that kind of configuration. You give me something like this, and I try to pull on an aggregate of these things all tangled together, and all these strands are going to get tangled up. So I'm going to have some significant mechanical integrity with this branched copolymer. And in fact, many structural polymers do have this kind of behavior. Order in polymers, crystallization. Everything, including long-chain polymers, want to crystallize. Their minimum energy configuration will be in a crystal form. The problem is it's tough to do it when you have a long chain, just like it's tough to boil a bunch of spaghetti and pour it on a plate and have the spaghettis all come out of line. That's not going to happen very often. In fact, you probably have never seen it in your entire life, and you probably won't. And the same is true if you take a bunch of chain linear polymers, you mix them up, and they're just not going to easily crystallize, but they do want to. So what tends to happen is that the chain polymer, if it's a uniform chain, it will tend to wrap onto itself to form a folded chain that has local crystallization. These folded chains tend to get gathered together in blocks to produce an overall microstructure with what is called fringe micelles or other terms that are used. But basically what's happening is that you have regions of your solid that are crystalline, and then there are grain boundary-like regions in between them that are disorganized. The more crystalline the polymer is, the stronger it will tend to be, but also the more brittle, and perhaps it will have other properties. Perhaps it will lose its transparency with as crystallization happens. So very often commercial polymers will be sold with a specification on the degree of crystallinity, because the mechanical strength and sometimes the chemical properties and the optical properties will vary depending on how crystalline they are and how much of the volume of the material is made of these ordered arrangements and how much is made of these disordered arrangements. So if you're purchasing polymeric solids particularly for structural purposes, you very often will have a specification on the polymer that specifies what the degree of crystallinity is supposed to be, and that's of course controlled during processing. Chain polymeric solids are usually partially crystallized. Somewhere between 10 and 90% is really high for a chain polymer, but this is occasionally realized. Incidentally, if you have polymeric materials, complex organics, Sometimes if they come out of nature rather than you made them, or even if you made them, one of the biggest problems in many of these organic materials, molecules, is figuring out what the structure is. You may know that there's a distribution of species. You may know what the species are. You can chemically analyze for those. But getting the structure, how those species are actually arranged in a complex molecule, is a real challenge. About the only way to solve that problem with any chance of success is to force the polymer to crystallize. If the polymer crystallizes, you can get a diffraction pattern from it. From the diffraction pattern, you can determine, well, not uniquely, but you can determine how the atoms are configured to within certain bounds, and you can then work with models to find one that gives a precise match to the material. There are many examples in history of organic chemistry where the breakthrough in understanding what was really going on with some important molecule was when someone finally succeeded in crystallizing it. Because once it was crystallized, it was just a matter of time before intelligent people using X-ray diffraction or other techniques would be able to sort out what the structure was. The classic example of that is DNA. People worked on the structure of DNA for years and got nowhere until, oh, good God, I'm drawing a blank on her name. Woman at Pure University. You know the name? I'm sorry? Rosalind Franklin. That's exactly right. I apologize. Because she's the one who solved the problem. She crystallized DNA. They got a diffraction pattern from it, and I think it was 6 months later that Watson and Crick produced the structure of DNA and got it right, and subsequently we were able to document that. But once it was crystallized, that was really she's the one that deserves a Nobel Prize, because once these things are crystallized, and if anybody really wants to, it's only a matter of a very short time before they work out the structure. The real challenge is getting it into a form in which you can get the diffraction information that will tell you what the nature of that structure is. She actually passed away before the Nobel Prize was given on, otherwise she probably would have shared it. I don't know, the Nobel Committee is kind of a weird bunch sometimes. She certainly deserves the credit for solving DNA, because she's the one who crystallized it. And once you have it crystallized, and I'm not saying it's easy to figure out the structure from the diffraction pattern, but it's inevitable that you will if you work on it long enough. Thermoplastic polymers. Long-chain polymers are almost always thermoplastic, unless we cross-link them, I'll talk about in a minute, because they will tangle up with one another. They can slide over one another to deform, and it's rather difficult to get them more than fractionally crystallized. So if we take a cross-linked polymer in liquid form and solidify it, almost always it turns into a glassy random configuration. We'll soften back again when the temperature is raised, and that gives us a thermoplastic region in here where it's rather easily deformed, but remains semi-solid. The classic situation in forming a glass, as we talked last time, in the glass of these random polymers, if you come down from the melting point, you always want to crystallize. The crystallization can be a relatively slow process, an extremely slow process when you're talking about getting significant crystallization in some long-chain irregular polymer. And as a consequence, it's rather easy to cool the material down into the glassy region where it forms an amorphous material and becomes a glassy polymer. Network polymers. I'm going to talk about two kinds of network polymers, but the classic one is this. The first really successful commercial plastic was Bakelite. Came out of Germany in the 19th century and was the basis for the IG Farben chemical company, which for a long time was one of the largest in the world. Bakelite is basically benzene rings that are joined together by molecules that build bridges, replace the hydrogen and build bridges between the benzene rings. And since the benzene rings, these bridges are somewhat puckered, you can build a three-dimensional structure by just joining these benzene rings together. You can form this into various shapes, because if you've ever used Bakelite, it comes in the form of a little powder. The powder is a partially reacted benzene base. You then have a setting agent, which may be just heat. Heat it up, the benzene rings interact, bridge with one another, form a three-dimensional network, and the net result is that you have a plastic in the shape that you have molded it into, usually with some press and temperature to get into the right shape and to get the temperature up to make this reaction go. The resulting network polymers are easy to cast into complex shapes because it's just a powder. You pack into the shape and heat it up, and it reacts and forms. They're dimensionally stable and strong, and they're called thermosetting because while a chain polymer, when you heat it up, it tends to soften. These three-dimensional networks are tied into three-dimensional by strong chemical bonds once they're formed. So you heat up Bakelite and it does not soften. You keep heating it up and it will eventually burn or decompose, but it doesn't soften like a thermoplastic polymer will. It does soften a bit, but not to the form that can easily work. And as a consequence, these are thermosetting. They are very easy to manufacture in the complex shapes, very inexpensive, and that was really the basis of the plastics industry. Phenol formaldehyde is what it's called. The other kind of network polymer we have is one of the most important in the history of technology. These are cross-linked polymers, where we take a chain polymer and we use reactions to build cross-links, periodic bonds between the chains. The most famous of all of the cross-linked polymers, and it's accidental discovery of something you probably heard in high school, is vulcanized rubber. Charles Goodyear, who the legend is accidentally heated rubber with a bit of sulfur. And what he found when he got through with it was that the gummy rubber, which you could deform into various shapes with your fingers, suddenly became a resilient elastomeric solid. Now, that had enormous implications in the history of technology. If you ask yourself, what was the key invention that caused us to drive automobiles instead of railroads? The key invention was not the internal combustion engine that had been around for a while. Steam engine. People made cars out of steam, Stanley Steamer. We had engines to make cars. What we did not have to make cars was tires. Imagine if all of the cars we were driving around had wagon wheels, wooden spokes with steel rims. Do you know how long the roads would last out here? We would be basically in the place people were in the